start the recording. Okay. Okay.
All right. Welcome everyone to our AI at AU forum. And this week we have an excellent speaker with us, Professor Mohit Bansal from the Department of Computer Science at University of North Carolina at Chapel Hill. And his talk is going to be titled Multimodal LLMs, which is large language models, unification, efficiency, and explainability. I bet like a lot of people know Mohit very well, but then it's my job to actually read his bio before he actually formally gives his presentation. So bear with me. Dr. Mohit Bansal is the John R. and Louis S. Parker Professor and the Director of MEWAR-GE Lab, UNC Chapel Hill, in the Computer Science Department in North Carolina, University of North Carolina, Chapel Hill. Prior to this, he was a research assistant professor, 3-year endowed position at TTI Chicago. He received his PhD from UC Berkeley in 2013. That's even before I started my PhD. And his BTech from IIT Kanpur in 2008. His research expertise is in natural language processing, multimodal machine learning with a particular focus on grounded and embodied semantics, language generation and question and answering dialogue, and interpretable and generalizable deep learning. He's a recipient of a lot of awards, DARPA Director's Fellowship, NSF Career Award, Google Focused Research Award, Microsoft Investigator Fellowship, Army Young Investigator Award, DARPA Young Faculty Award.
You can skip them. Yeah, feel free to skip them.
I'm pretty sure like you have already skipped small awards as well. And then outstanding paper awards at ACL, CVPR, ESL, you name it, okay? And something that is not in his bio, I will tell you. So he got promoted, probably we can call it double promoted. Within just 1 year, he became a full professor, and you will see after his talk why that happened. So without further delay, I will delegate to Mohit. So welcome, Mohit, and
thanks.
This is now the floor is yours.
Yeah, thanks for the kind introduction. Yeah, I'm really happy to be able to talk to you all. Hopefully, I'll also come in person in the near future. We were just discussing the post-COVID like travel ramp up, and also have 2 international travels coming up in 3 days. So yeah, but I'll try to come see you all soon. So yeah, so today I'll be talking about multimodal generative LLMs, and I'll focus on 3 aspects: unification, interpretability, and evaluation. And hopefully all of you have been seeing a lot of multimodal large language models around you now, right? That's sort of where the field is moving. We've been doing it for the last probably more than 10 years. So let me give you a sort of brief journey on this whole aspect of what multimodal LLMs and their generative counterparts mean. And more importantly, 3 things that I think are really important for the field in terms of these models, which is unification, how to make them interpretable through planning and programming, and then also a really important aspect of how to evaluate these things, because we know that even language generation, right, is super hard to evaluate, and it's very open-ended. So imagine how hard multimodal and visual generation is. So I'll go through this as the talk outline, right? So the 3 parts will be unified multimodal learning, right, which allows also the bonuses of generalizability, shared knowledge, and efficiency. Then I'll go into the interpretability part and controllability part, as I mentioned, through planning and programming with LLMs. And then finally, a little bit on the evaluation side. And then I'll end with the next big challenges as 1 slide to brainstorm about. So very quick background. I'll assume most of the room, right, already is aware of what large language models are and a little bit of multimodal versions of these. But just to give a brief recap, the whole idea of large language models and the pre-training fine-tuning setup is as follows, right? The idea here was that the motivation is that the large amount of data, right, that's needed for these models is obviously not available and pretty limited, right, in downstream tasks, whereas pre-training enables much more data. So in the vision side, what this would mean is that you could take something like ImageNet, right, which has 1.3 million images, and you could do a more cheaper sort of self-supervision kind of task or an image classification kind of task, right? But then when you went to the fine-tuning downstream task, right, then you could have something smaller and more complicated annotations, for example, object detection or other things. And then you would basically use that pre-trained model and then fine-tune it for the downstream tasks. Same thing, right, we were doing in language, where you could take all of the text in Wikipedia, say 2,500 million tokens, right? And then you could use the masked language modeling kind of self-supervision pre-training objective, right? Where you mask certain words, or I call it a fill in the blank task, right? So you can mask certain blanks and then ask the model to predict the blanks, right? So that gives you a lot of supervision, right? To be able to train a pre-trained model with some architecture like transformers or several other architectures. And then again, for fine-tuning, you would basically take a smaller amount of more sophisticated or complicated annotations, right, for downstream, more complex tasks like movie review, sentiment analysis, classification, and so on. And then you fine-tune your pre-trained model on that. So this is where I start motivating why you need similar things for multimodality, right? Not just vision alone or language alone, because the idea is that if all of these things were just independent of each other and not aware of each other, right, then you would have a visual pre-training kind of pipeline and then a language pre-training pipeline. And then early on, what people would do is, right, like basically the limitation, like I said, would be, right, that these single modal pre-trained models will not be aware of the interactions between vision and language. So what early approaches would do is do late fusion, right, where they would basically take these pre-trained models that have been pre-trained without being aware of each other, and then just try to add late fusion kind of layers, right, to bring them together, maybe, right, combine their parameters, and then try to apply them to a task like visual question answering or navigation. Excuse me. So yeah, so then that's where we sort of came up with, this is already 5 years ago, but this was one of the first multimodal pre-trained models. So you can think of it as a BERT kind of model, but for vision and language together. So the idea of LexMERT, large-scale cross-modal pre-training, was that it wants to, like I said, combine knowledge from text, vision, and cross-modal matching. And the way to do that would be that you would have 3 encoders. One is for the language, which we already know, right? You basically, like BERT, would have masked language modeling to basically pre-train the language encoder. And then you would also have something similar on the vision side, where you would do masked image modeling instead of masked language modeling. And these different patches of the image would get masked, and you could do it as a region of interest features or position features. And this would help you pre-train the object relation encoder. But then more importantly, you would also have a third encoder, which is the cross-modal encoder. And the cross-modal encoder gets 5 different kinds of pre-training tasks. Some of them can just be the pure vision and the pure language kind of pre-training tasks. But more importantly, you also need cross-modality matching or image question answering kind of pre-training tasks to train this cross-modality encoder, so that it is basically being trained on tasks that need you to be aware of both the language and the vision side. So something like fill in the blanks, but by conditioning on the image, right? Or fill in the image, but by conditioning on the language. Or image and caption pairing, right? True or false for positive or negative pairs, or question answering on images. So different kinds of pre-training objectives were added here. So this was, like I said, the first kind of approach for converting pre-trained large models, right, to multimodal scenario. And as expected, it got very big gains at that time on a lot of the multimodal tasks, like the VQA leaderboard, the NLVR2, which is a image relationship kind of task, where you're given 2 or 3 images and you have to sort of do relationship understanding between them. Like one of the relationships could be there is only 2 of these 3 images that contains a red ball on the left side of a blue stack of cubes, right? Or only one of the 3 images, right, has this property, or all the 3 images have this property. So it asks for these kinds of complex questions. And then VisVis was another interesting example. It's kind of like VQA, but more in the real world, where people with visual disability could basically have out of focus or out of camera or sort of blurry images from their phone, and they're trying to ask questions about like the expiry date on something, or the color of something, or how much is like the money, the bill, is it a $10 bill or a €10 bill, and so on. So there's also a good application where these kinds of models got big improvements. So anyway, that was more like a kind of brief historical context in some sense, right? I mean, I know it sounds weird to say historical for 5 years, but as you probably are aware, since then, there's at least maybe 800, 900, if not more models, right, that have already come up, which are a lot of specialized vision language pre-training models. So, I mean, I'm just giving a very short kind of timeline here, and it's not even, it's only till 2021. So what I'm trying to motivate is the first unified model now, right? Why do we want to move away from a lot of over specialized models, which means that they could have different architectures, single stream, combining vision language, or multiple streams, and then doing cross attention, different kinds of objective functions, different kinds of pre-training data, different kinds of attention modules, right? So all of these models were like very specialized and different from each other. And sometimes they're also very specialized to the kind of multimodal task they're trying to do. So what I'm trying to motivate here is why we want to unify all of this into a single model that can handle all of these tasks with the same architecture, same objective function, same pre-training data, right? Same set of parameters. But you also get the free bonus of not just being generalizable to other tasks, but also efficiency, right? Because you're sharing parameters, and you're also being able to handle unseen scenarios. And like I said in the very beginning, you also get shared knowledge. So they actually also help each other, right? So there's sort of three advantages here of unification. So I'll give this kind of journey here of more and more unification as we go downwards. So first, we'll start with unification by treating all the tasks as text generation. This was the first unified model. Back in, we started this in 2020. A lot of the more later models, right, cited and built on top of this and did more interesting unifications. Then we moved on to whether we can also unify the video and audio modalities. And then can we also bring layout into the picture and handle documents, not just multimodal tasks of image and language. And finally, we look at Cody, which basically can take any combinations of inputs and outputs instead of hard coding what the input and output should be. So let's start with VLT5. Like I said, here the idea was that you have very, very diverse kinds of vision and language tasks, right? For example, VQA is image plus question, and the model has to generate an answer. And this is usually a 1000 kind of classification task. You already know the vocabulary of the answers and you have to choose the best answer. Then something like visual grounding is basically given an image and a grounding expression, referring expression. You have to actually ground that expression in one part of the image. So as a bounding box or like a segmentation map. Then you could have something like image captioning, which is obvious, right? Image to caption, description. And then you could also have something like multimodal machine translation, which is image plus one language, right, to another language, where the image can be a bridge. So like I said, the problem with the task-specific architectures or objectives was that each of these tasks was being treated as very different models and setups, right? So something like question answering, visual question answering would have the image and question inputs, and then some kind of specialized VL transformer, but then the output would also be a VQA head, which is a sigmoid over top K answers. Whereas in visual grounding, where you have to predict the bounding box, right, it would be more like a different transformer here, but then also the output would be a region scoring head, and then a softmax, right, over different regions or boxes. And then you can imagine, right, the multimodal machine translation, captioning, all of these will, right, have their own specialized architectures. So 3 years ago, right, we were asking this question: can we tackle all these vision and language tasks with a single objective and unify them together, such that, like I said, you also get some generalizability, shared knowledge, and efficiency? So the answer was yes, we can do something which we call VLT5, Vision Language T5 model, where we are treating all the multimodal tasks as text generation. So let me give you some examples here, right? If it's the task of multimodal sort of fill in the blanks, right? Which is a dash is dash over fire hydrant given the image, then obviously it can be done as text generation, right? The decoder can generate man and jumping as the two fill in the blanks. If it's visual question answering, yes, then also the output can be generated as text. Instead of classifying the 1000 answers, you can try to generate the answer. Visual grounding is interesting. So where the job is to take the referring expression and find the box, right, that refers to this expression, that this expression is referring to. So there also, instead of selecting and doing the region scoring head, you can actually try to generate the label of the bounding box as text, right? And then others are even more obvious, right, where image text matching can be true or false. So again, as instead of classification, you could do it as generation. Multimodal machine translation and captioning, right, should also make sense of how they can be handled as text generation. So pretty much that's the basic idea, right, of VLT5. We said we can basically have this unified architecture where there's a task name. This was one like an early example of task prompting. Then you have the language input of the task, the visual input of the task, and then you feed all of this in a bidirectional multimodal encoder single stream. And then the output is an autoregressive text decoder, which in this case, since you're doing language grounding, would be generating the label or the ID of the bounding box. But in other cases, right, you would do other things. So basically, you can think of it as multimodal conditional language modeling. So now just to give you a brief picture of how everything gets unified, right? So the top blue part is always showing the previous specialized models. So in this case, I already told you how VQA and visual grounding operate, right? So VQA head versus region scoring head. But at the bottom, you can see our version where everything can be treated, right, just as task prefix, vision input, language input, and then all of this becomes text generation, right, instead of any specialization. And then there's two other examples, right? So NLVR2, as I told you, is a task where you give different images and you have to answer some sort of relationship or entailment or property kind of question on these images. Only one of these two images has certain properties, something like that. So here again, you can imagine that the previous models have very specialized architectures, binary classification, two transformers, each taking like different text and image regions. But in our version, right, you can just feed all of the image regions or the visual part of the input, the task name, the text, and then again, generate true or false as text generation. And then translation also is the same thing, right? You will basically have vision input, language input, task prefix will also mention the languages being translated to and from, and then generate the other language also through the same text decoder. So everything can be unified with this setup. Just to give you some brief results here, I'll not go into too much detail because I want to focus more on the new parts, but the basic idea with 3 takeaways. One is that VLT5 without any specialized architectures for individual tasks can perform similarly to any sort of specialized architectures for these tasks. More importantly, it can share all the parameters across the 7 tasks that we studied. And with 1/7 of the parameters, right, it can still obtain pretty reasonable and comparable performance to the unshared setting where each task can learn its own parameters, but then there's 7 times more parameters. So suppose instead of 1 billion, you have to handle 7 billion parameters, right? And so as I mentioned, this was sort of the main takeaway here, right, of sharing knowledge and being efficient. And then there were several useful follow-up works like SimVLM, Flamingo, Unicorn, Unified IO from Google, Meta, AI2, a lot of these that cited and built on top of VLT5. And there were other things, right? Then we started adding like vision also as part of the output. So text and vision can be generated automatically. Instead of just generating the bounding box ID, you could also start generating the layout coordinates, right? The coordinates of the box and so on. And then the last advantage of such a generative kind of decoder text generation model was that you can also handle rare categories better, right? Because instead of classifying something, now you're generating things piece by piece. So rare answers or unseen answers, right, have a better chance of getting generated. So that was sort of like the older part, right? The first kind of unified model that we did 3 years ago. Since then, we started trying to make things more and more unified. So you might notice that, right, in VLT5, even though the output is very nicely generalized, right, the input is still handling images through a separate image encoder and the text is treated separately and so on. So then in NeurIPS 2022, TVLT, which was called Textless Vision Language Transformer, we decided to see whether we can have the same encoder for both vision and language. So the way we did that was we actually we first tried to investigate whether we can just get rid of text completely, right? And what is the advantage of that? The advantage is that when you're trying to do tasks which are, for example, video question answering, right? Question answering on videos or video captioning and these kinds of tasks, it's pretty painful to be able to have, like, you have to basically run automatic speech recognition, right, on the videos. And then that is very noisy output. So the subtitles and all of that, right, is pretty noisy and unaligned, misaligned with the video. So if you go textless, which means that why don't you treat language as direct audio, not even go to the text modality, right? So this is a lot of advantage because first of all, you skip all the errors from the ASR module. You skip all the delays, right? It's a very slow process to get all the ASR outputs. You skip that. And you also don't need to rely on all the text modules like tokenizers and other things, right? Which usually are also very brittle and not really generalizable, and they're not even available, right? High quality tokenizers may not be available for a lot of domains and languages. So that's sort of the goal here, right? That if we can unify vision and language and treat the language as audio, you actually first can have a homogeneous vision language transformer that I'll talk about next, right? Where you can actually have the same exact masked autoencoding by treating audio as images. And you also get 30 times inference speed, no requirement of text modules, as well as only 1/3 of the parameters. So this is the main sort of technical novelty behind this. What you can do is if you're treating language through audio, now you can actually treat both the audio and the images from the video exactly as the same. So both of them can be treated as images, and you can basically do masked autoencoding of image patches on both the audio and the images, right? So that's what I've shown here, right? You can do a unified vision transformer VIT style patch embeddings for both the video and the audio inputs. And on the output side, right, you can have basically a multimodal. So the encoder is multimodal joint encoder, and the decoder is basically keeping the separate generations for audio and vision because, right, they are different modalities. But since we are treating both of them as images, you can share the decoder weights too. And then the objective functions are the usual two popular objective functions. One is the masked autoencoding that I already mentioned, right? The patch reconstruction. And the contrastive learning is the objective function of just taking pairs of positive video and audio and negative video and audio pairs, right? And asking the model to separate the two with a big margin. So yeah, so the results were pretty exciting to the community. We basically showed that without using any text or any text modules, just directly starting with the audio, you can actually get almost similar performance to text-based models on very diverse tasks. So you can have things like image retrieval, video retrieval, visual question answering, but also you actually get better results on tasks like multimodal sentiment analysis and emotion analysis, right? Because their audio has even more useful features. So you can maintain sort of text performance while getting better on tasks that do need some right audio features, while, like I said, being 30 times faster and 1/3 of the parameters, as well as being able to have the same exact right architecture and objective functions. So here it gives you some quick examples of the masked reconstruction that I was talking about. So on the image side, right, you can do this kind of masking and ask the model to reconstruct the image, and it gets pretty close to the original ground truth images. And then on the audio side, which is representing language or text here, right, you can also do masked patches of the spectrogram and ask it to reconstruct it, right, and then get pretty close results to the original spectrograms. So that was the second level of unification. Now, the third level is where we said, okay, how do we handle things like documents, right, where text, images, handwritten things, logos, right, tables, everything is in the same input. So for that, right, you need even one more level of unification where image, text, and layouts, right, should all be treated with a single architecture. So this was CVPR 2023 called UDOP, which is Unifying Vision Text Layout for Universal Document Processing. Here, the idea was, like I've written here, right, is that you want to unify text, image, and layout modalities, and you can do it with various task formats, like I'll show in this figure. And you can actually do both document understanding as well as generation or editing of documents. So basically, the idea is that if you want to understand the content of documents better, you can actually do it in a more strong way if you also, your model is also capable of generating and editing documents. So this is the idea of the UDOP model, which is a joint vision, text, and layout transformer. And the idea here is that, like I said, UDOP also learns to generate and edit document images, again, via masked image reconstruction. So the idea is you might be given this kind of like utility bill or some sort of document as a printout kind of image. And you have these various pre-training tasks that we add to the model. So it could be a vision-only task, like the red ones, masked image reconstruction. It could be a text-only task, like visual text recognition of the image, of some part of the image, or question answering on the document, the text part. But it can also be a layout task, which means that you have to basically model and reconstruct the layout, by which I mean coordinates, right? So what is the position of different elements in the document is basically called layout reconstruction. But the best part is you can also have mixed tasks, where I can do text reconstruction with layout. So I can ask the model to, I can hide some part of the text and ask the model to reconstruct it along with the layout, the position, right, and the coordinates that it used to be present in. So this, right, you can understand that it teaches the model not just how to reconstruct the text that's missing, but also understand where was this text supposed to be present. So this gives you a lot of the model learns a lot of important features about which text is more important in which position, and what does it usually mean if a certain text is in the left side of the document, or bottom right is a signature, like left bottom would be the signature, right top center would usually be a logo, right? Those kinds of things. So yeah, so this is in some sense the summary of UDOP, right? That you can have a unified encoder that handles vision, text, and layout together. And then on the decoder side, text and layout get generated together as a reconstruction, and then the image parts get reconstructed separately, but you can still share the parameters in between all of these. So this led to getting the state-of-the-art and rank 1 on this very popular benchmark called DUE, Document Understanding Benchmark, which I think on 8 of the document AI tasks, UDOP gets good improvements, and it contains very diverse documents from domains like finance reports, academic papers, right from like bioRxiv and PubMed and archive, and then also website kind of documents. And the tasks are things like I said, question answering on different parts of the document, or extraction of information, or even NLI, right, entailment and QA kind of tasks for tables, and so on. And the most exciting part here, as I said, is that the model is so strong, is that instead of just trying to understand things, it's trying to understand by generating and editing. So this gives you some power of the decoder example here, where what I can do is I can basically ask it to take a certain part of the document, like the logo or the title, and replace it with whatever I want in the exact same font, exact same ink. I can also ask it to add text in a random location, and you can see it can match the printer, ink, and format and everything. I can also ask it to replace certain thing in the documents with other things like UDOP, proposal by UDOP instead of proposal by someone else. I can also ask it to change serial numbers. So obviously, we did not release this decoder, right? It's more a decoder that's helping improve the encoder. And we purposely did not release this, right? So that there is no misuse of this kind of decoder as a standalone right demo. It should be more how to improve your understanding models, right? By having decoders that can generate and edit documents. And then the last piece of this unification is where we say, okay, like all of these current unifications that we propose to the community, right? All of them are still sort of manually deciding, right, which inputs to take in, which outputs to generate, more again in the sense of like what kind of things they are meant for. But what if we wanted a unification model that can take any combinations of input modalities on the fly, right? Even if it's not trained for that, and also generate any other combination of output modalities, again, so even if it hasn't done that during training, right? So that's the thing that we have looked at in Cody, which is upcoming at NeurIPS in December. So the idea of Cody, let me show you some demo first. Can people hear the audio? So when I play this, do you hear any sounds?
So on Zoom we do, but I don't know what about the like in-person audience. Cheryl, can you chime in?
Yeah, so I'll wait for someone in the room.
Yes, we can hear.
Okay, great. Yeah, so the idea here is that, like I said, Cody can take any combination of input modalities and generate any other combination of output modalities. I'll give the demo first and then explain how is this possible in a technical way, because, right, you don't want exponential number of loss functions, or you also can't assume that you have training data for all these combinations. But let's look at its capabilities first. So here, what I can say, yeah, so this is just the demo. So what I can say is, okay, so now you see, right, you hear this audio clip with the rain ambience, and you have a sentence maybe saying teddy bear on a skateboard. We don't do real people just for ethical purposes. So we'll have some teddy bear and polar bear and koala bear examples and panda examples. But there also can be like an image, for example, of say New York Times Square, right? And now I can say, okay, here are some of the inputs I gave you. Now I'll say, hey, Cody, take this audio input and give me an image input, or give me a sentence input. So in this case, I'll say sentence input, so output, sorry. Then I can say for the red part, I'm saying now take the image and the audio and maybe generate another audio for me. So now you can see, right, that the audio is actually both combining the street noise and some of the raining sound and dripping of water and stuff. Then for purple one, I'll say, okay, why don't you do something even more complex? Take the image, the sentence, and the audio, and try to generate some image, right, that combines all this information. So then what it will do is it will generate this kind of image. And here you can see that the teddy bear is on a skateboard. The floor is wet because it's raining, and you see Times Square kind of background in the image. Now I can say generate a video plus audio. This was probably the most complicated part. And here you can see that, first of all, it's raining. The teddy bear is not completely accurate, but it's coming on a skateboard. There's some sort of noisy street or Times Square in the background, right? But the best part is you hear three sounds. You hear the rain sound and street sound, but because we said teddy bear on a skateboard, you also hear the clicking sound of the skateboard, right? Let me play one last time. So this is sort of the capability of Kodi. I mean, we also have a lot of other examples here. Let me just show you. So yeah, what I mean, for example, I could do is I could basically give an audio clip, and it's just a piano audio clip. So the model will understand this talking about a piano, and there's an image of a forest. And if I ask it to say, hey, take audio plus image and generate text plus image, it will generate this caption of playing piano in a forest and put this piano and a person in the middle of a similar looking forest, right? Or I can say something like, I'll say oil painting, cosmic horror painting, right? Some description of the style of the art. And then I'll just give it some sound, right, of water and sea and ocean. And it can try to generate a horror kind of ship painting. More interestingly, I can say something, let me see. Yeah, I could generate this. I can say eating on a coffee table, and I'm saying you take the text and this image and generate me a video. So it can basically take the panda image and the sentence eating on a coffee table and try to generate the combination. So anyway, I'll not have time to do too many examples, but you can browse through the demo page later. But now let's look at the technical issues here, right? So the reason, so like I said, first of all, Kodi is a new kind of generative AI model that can take any combination of input modalities and generate any other different combination of output modalities. For example, taking some combination between text, audio, image, video, and so on. This can easily be extended to other things. Right, like layout or other kinds of modalities. And the idea is that, right, we want to do different kinds of, for example, an application would be creating very different, diverse, many modal stories. But technically, the problem is that you cannot train such a model without significant cost, because the number of right combinations for input and output modalities will scale exponentially. And your training data sets are also missing, right? For most of these combinations, you don't really have any high quality data for many of these combinations that we are asking it to generate. Right. So the technical idea here we proposed is called bridging alignment, which basically gives us a way to efficiently model these exponential number of input-output combinations, but only with a linear number of training objectives, such that it allows you to generate any input-output combination. So the way we do it is there's two stages. One is the composable conditioning stage, and then the second stage is the joint generation. So for stage one, which is composable conditioning, first you train a latent diffusion model for each modality, right? So this is trained independently so that you can ensure high quality generation, right, for each modality. Right, because this is an important part. And then for conditional generation, right, what you can do is, for example, if the input is supposed to be audio plus language and the output is supposed to be image, so these input modality LDMs, right, they can be projected into a shared feature space. And then the output LDM for the image will basically attend, right, it will do attention on the combination of these input features in that shared feature space. So, right, a simple idea that you first train independent LDMs, then you have a part where you can project them into a shared feature space, and then the output LDM is extracting or attending or doing attention and taking out features from the shared space, right? So this first part allows you to condition on any combination of modalities, right, input modalities, without directly training for such settings. And then you do something similar for the output side to get different output combinations, where you add a cross-attention module to each LDM and an environment encoder, right? And then you basically project the latent variable of these LDMs into a shared space. So now you're doing the inverse, right? Where you basically have a cross-attention module and an environment encoder, and you project, right, into a shared space. So basically this allows you again to have a different kind of diverse combination of output modalities that you can generate without training on all the generation combinations. So it's a very cheap kind of efficient way to be able to handle any new combination of input modalities, and output modality combinations can also attend to any different kinds of input modalities. So I already went through these examples here. So I'll skip most of these and you can see this on the website. Yeah, I think I'm on time. So let me move on to the second part of the talk, which is about how to make. So we first, till this point, right, discussed a lot of unification ideas, right? How can we make different kinds of specialized vision and language tasks be handled by a very centralized, unified kind of architecture, such that you get generalizability, combinations, efficiency, right, with shared parameters as well as shared knowledge. Now, stepping to the second part of the talk, we want to look at how can you actually make this process more interpretable and controllable, right? Because right now, if you remember, most of these models that you're looking at, right, that can do image generation or any kind of similar task, you don't really know what's going on behind the scenes. And you also, that for the same reason, cannot control it. So that's why in this part, we are going to have a theme of, can we use language models, right? Large language models like GPT-4 to first come up with interpretable plans or programs, right, for doing some kind of multimodal generation task. And then this way, you also know how this output was created step by step as a program or a plan. And you can actually have more control by changing different parts of the plan, also allowing human in the loop, right? Because the human can come and fix or change certain parts of the plan, saying, no, I want this here instead of this, or I want to correct this part because this is where most of the errors are happening, and so on. So we'll look at how this language model-based planning or programming can help things like image generation, multi-scene video generation, as well as diagram generation. So I'll focus more on the first part and then second part also, and then I'll mostly just give a very brief look at the third part. So this is the motivation. Once again, the idea is that if you're doing text to image generation, right, you have a generation model like DALL-E, Imagine, Stable Diffusion, and so on, right, for some input like 2 Pikachus on a table. But you have pretty much no clue, right, what happened here, why did it generate this kind of image, where did it go wrong, right, how did the model decide the layouts, and so on. And in fact, the same thing happens for evaluation. Right? When you're trying to evaluate a generated image, you just put it in some sort of black box model and get a score, but you again don't really know how this score was computed. So at the last part of the talk, we'll also look at evaluation and how to make evaluation more interpretable. But for now, let's just focus on the text generation part. So the idea here is that this is all sort of inspired from a lot of work like neural modular networks, right, and visual programming, where the idea is that you first define a lot of visual modules for different things like location, face detection, segmentation, selection, classification, right, so on. And then you generate a program with a large language model on these modules, and then you can execute that program, right, to actually get the answer. So recently, this was done for, say, something like visual reasoning or visual question answering. We are doing it for the first time for something like image generation, right? Instead of understanding, we are looking at generation tasks. And there's a long history of similar work here, right? Like it goes all the way back to neural modular networks, right? Summarization programs, and so on. So coming back to what VP Gen is supposed to do, right? What its main goal is that I don't know why the PowerPoint is moving on its own, but the idea is that you want to first, you have 3 steps, right? So if you get the caption 2 Pikachus on a table, you first want to do object and count generation. So this is the prompt, right, to the large language model that given the caption, generate me the objects and their counts, right? So 2 Pikachus on a table would be generating Pikachu 2 and table 1. Then it will ask the model to generate the layout, which means that given the caption and the objects from the previous turn, now also tell me their coordinates, right? So 2 Pikachus on a table and then Pikachu 2, table 1. Now the language model is trained to generate the coordinates of the 2 Pikachu boxes as well as the table. And the way it learns this is we give it a few examples, right, of these programs as in context learning, but it also has knowledge in the large language model about what prepositions like on mean or to mean, right? So it actually learns through this combination of language understanding and some examples that something X on Y usually means that the coordinates of the second thing, right, should be lower on the Y-axis than the coordinates of the first thing, right, which is on something. And then finally, once you have these layouts, you send it to a layout to image generation model, which basically tries to convert this layouts from the middle step to an actual image by using in-painting, right? So it's infilling the different boxes with the objects that it's supposed to generate in those boxes. So this is the idea of VP-Gen, which means visual programming for step-by-step image generation. And in terms of the results of this process, we show in the paper, there's more details here, but I'll give a brief summary here, is that you basically see that you can get large improvements on things like spatial control. So counting, right? So Gen is built on Stable Diffusion 1.4. So that's the most comparable baseline. You can get huge improvements on counting, right? Almost 25%. You can also get more than 30% on spatial skills, which means put something to the left of something or the right of something, right? Stable Diffusion is pretty bad at that. But based on this controllable program model, like the VP-Gen thing that I just showed, you can get much more control and correctness on the spatial relationships, and also a little bit improvements on scale, which means that something generate a cat bigger than the dog, right? Those kinds of things. So that's one sort of conclusion here. The other thing I'll show briefly is the analysis of VP-Gen and where its errors are. So we took a sample of VP-Gen output generations, and we manually checked which step was doing the most errors. So in fact, we found that the first step where Vicuna or ChatGPT, right, tried to generate the programs, that's almost always correct. So the layouts and the programs are very high accuracy, and the most of the error is coming from the second part, where we take an off-the-shelf layout to image generation model like GlyGen, and 35% of the time it's not able to understand the layout enough to generate the correct image, right? But there's also good news, because GlyGen kind of models, right, will keep getting updated for layout to image generation. So that was sort of the programmable part for images. Now we have done some sort of recent breakthrough work on being able to also do this for video generation, right? So this is, as you can imagine, a very complex task, because most video generation papers that you'll see are about taking a very single scene, single action, or single sort of event, right, or scene kind of situation, generating the image for it, and then maybe adding a little bit of motion to it, right? But there's been no work on looking at multiple scenes of a long video, right, where you're trying to build a whole story of, like, say, how to bake a peach cake, right, starting with all the way from the peaches to the flour to the kneading of the dough to the oven, right, to the eating, all of that, the washing, right? But as you can imagine, the challenge there is that if you do a current kind of video generation model for this, or even an image generation model, all of these scenes that I'm describing will all look very different, right? The person will look different, the kitchen will look different, the utensils will look different. So the biggest challenge here is, can we use a large language model to plan a multi-scene video such that it's not just planning the layouts of each scene, as we showed in VP-Gen, but in this case also planning the consistency, which means that let it decide which objects in the foreground should be the same cluster and which objects in the background should be the same cluster. And then maybe we should start a new cluster when something new happens, right? So think of it like co-reference resolution kind of NLP work, where you're always deciding these co-reference clusters, right? When I mention a new pronoun, like he did something or she did something, now we need to decide whether the he refers to a previous cluster of entities, or is it starting a new, right, cluster, that kind of thing. So let me give a brief teaser for this work. So the idea is you start with a single input prompt, right? And then, so we can handle something which is a very high level single prompt. It will automatically break, right? So what we'll do is we'll take a prompt like a hungry cat is finding food. And then first the GPT-4 kind of LLM creates a video plan, which means that it will describe all the scenes step by step. It will generate all the entities and their layouts. It will also generate the backgrounds for each scene and the groupings, like I said, the consistency groupings. And then the second part, which is the layout to video generator, takes this video plan, and then it will try to basically extend something like GlyGen, which is layout to image generation. It will add guided 2D attention to it to basically take the layouts and the consistency groupings from the first stage and generate each frame of the video, right, such that it can respect the layouts as well as the consistency. So this is a more detailed version of the same thing, right? A prompt goes in, the video planner takes the prompt and generates, say, suppose we are creating 3 scenes here as an example. the first scene description will be created, right? A hungry cat is finding food. So cat is lying down on a bed is the first scene. It will also generate the different entities in different colors, which is reflecting their consistency grouping as well as their positions, right? Then the second, and then it will also tell you the background is a bedroom. Then it will generate the second scene, which is then she gets up, right? So then it will still use the same two entities of the cat and the bed, but then the locations you can see have changed because now something is getting up, right? So the Y coordinates and some other things will change. The background is still bedroom. And then the third one is she goes to the kitchen to eat a snack. So now a third entity starts, which is a gourmet cat snack, right? Which is a different color and a different consistency grouping. And the location, like the layout has changed as well as the background location. So this is a toy example, right? A mini example of what's going on behind the scenes. And then this scene goes in to the second part, right? The whole video plan that we generated goes to the video generator. And then for each scene, it takes the scene description and the layout and consistency groupings, right? That was created in the first part. Now I'm showing it in a more visual way with the colors and the boxes, right? And then it uses our module called layout to vid, which is basically extending Glygen, right? To add these guided 2D attention models to finally generate the video. And this is a little bit more detail on the layout to video generation, where the idea is that you start with something like model scopes, spatiotemporal block, and you basically add guided 2D attention here, which is what we do, inspired by Glygen. And the main idea here is that you basically have guided 2D attention, which takes in layout information for fine-grained object control. So this is the module that we've inserted, which can basically take the layout as well as the text and allow you to do fine-grained control in the video generation process. And the best part is you only update these parameters. So it's also very efficient. We only update these attention parameters, the 2D attention. And we also make sure that the parameters of each box, right, which is belonging to the same grouping, consistency grouping, also shares parameters. So now let me show you some quick examples. This is a multi-sentence to multi-scene video example where left side is a baseline model and right side is ours, right? So it's about mouse is holding a book, happy face, pulling petals of the flower, holding flower by his right paw, right? So as you can see here, I mean, the left side keeps changing the scene and the mouse is not even right the same most of the time. Whereas on the right side, you can see the mouse is consistent. It's also actually following a lot of these very complex unseen actions like pulling petals and holding in the right paw. This one is another example about dog snowing, singing, dancing, where the dog is consistent, right? And it's also trying to respect all the actions and the layouts that we are saying. This is another more complex example where we don't give multiple sentences. We actually just give the high-level single sentence. And we ask the model to already predict all the intermediate steps as well as generate the video. So again, on the left side, you will see all the inconsistencies, but on the right side, you will see that the person's green apron and the utensils and the background kitchen, right? They are much more consistent as well as trying to follow the layouts. Same thing for making peach melba, right? So it's automatically deciding all the steps needed to make peach melba, but also building consistency. Then we did more fine-grained analysis of actions, right? Directions, left, right. Can our model understand all this? And also accurate layouts. And finally, it can also do something like user input-based video generation. So if I have a story like X gets up from the bed, X goes to the kitchen, eats a can of food, X sits next to the window, I can keep changing X. First, if I give it a cat, then on the left side, you're seeing the example for the cat, right? The cat is basically going, getting up, eating something in the kitchen, then sitting on the window. And then on the right side, you will see the same thing is happening with a teddy bear that I gave as input, right? So it gets up from the bed, it goes and eats a cake, and it's basically able to then go and sit on the window. So you can also do user-defined inputs. Okay, so I want to keep the last 5-6 minutes for evaluation, so I'll skip most of this part, but this is the diagram, this was the video generation. And then the last example here is for layout planning is something we call Diagrammer GPT. And here the idea is that can we extend something like VP-Gen, which is right for generic images of people and teddy bears and animals, to something very complicated and fine-grained like diagrams, right? So you can imagine this has a lot of applications in education and anyone who's trying to visualize some complex concept, right, into a diagram. So we have an NSF AI Institute on engagement and in education. And so the idea here is that can we have something where a student or a teacher, right, can take a very complex kind of concept, right, like a diagram showing the Earth revolving around the sun 4 times, each of these solstice, equinox, right, a lot of that. And can it generate some kind of initial diagram, right? We are not claiming that this should be, right, replacing humans or not have human in the loop. The idea is that it can use our LLM-based programming approach to first create a diagram plan using GPT-4 or any strong large language model, which can then be visualized, right? This is the initial plan visualization. It can also have some iterations with feedback from another model. And then it can give you that initial diagram, both the layout and the image on PowerPoint, Inkscape, Adobe Illustrator, right? Many software. That's why we call it open domain and open platform. And then the user can come in and say, okay, this layout is good enough, and I'll use this image. Or they'll say, no, there was this one arrow that has an error. So then they can fix it on PowerPoint or any platform, and then the model can generate the corrected image. So that's sort of the basic summary of this without going into the plan details again. But the idea here is, like I said, the diagram plan is generated. Then it creates the visualization of the layouts from the plan. Then there's some feedback that can improve it. And then the final diagram generation is again done using Glygen, updated version of Glygen that we call diagram Glygen, which is layout to image generation. And then I'll skip the more detailed versions here. But like I said, what you can do here is you can actually, so there's a lot of results in the paper, right, where this is actually better than all of the previous kind of models that can be used for diagram generation and human evaluation. But we also compare it to stable diffusions, bad diagrams, even DALI, something like DALI 3, which you see on the left here, looks very fancy, but everything is completely wrong here. Like Earth's layers are not supposed to look like a burger. All the words are wrong here. All the flowers were wrong here. There was not any rows instead of just columns. And then the human in the loop is the interesting part here, where, like I said, you can basically have your diagram rendered in any platform. And then, right, you have an input prompt, initial plan generation, initial diagram, then the user can give their edits, right? And then using the corrected layout, right, with the human in the loop, we can generate the corrected diagram. So that is probably the best application of this, right? Instead of obviously assuming that we will get perfect diagrams for every complex scenario. Okay, so in the last 5 minutes, let me focus on the evaluation part of multimodal generative LLMs. The idea here, like I said, is that this is a very understudied aspect, right? Imagine any of you who have worked on language generation, right? You already know that it's very hard to find good evaluation methods for language generation, right? Because if I'm generating a summary of a document, there can be thousands of correct summaries, right? So you need something that can understand paraphrasing and semantic concepts, right? And structure, right? Not just try to match the ground truth, because there can be many correct ground truths. So same thing is even harder, right, for image and video generation kind of tasks. So I'll give 2 examples of what we've done in this area. One is called DALI eval, which was the very first paper to do evaluation for image generation. So just in terms of background, right, to give you a little bit more motivation, before 2021, this is how image generation looked like, right? Not that good. So the evaluation metric is just focused on quality, which is something like FID or inception score. And the basics kind of logic behind FID is it tries to match the distribution, right, between the generated image and the training images. So this made sense back then, right, because we were not even close enough to the distribution of the training images. But then after that, since DALI 2, right, astronaut riding on a horse, armchairs in the shape of an avocado, the saturation of FID went very fast. Like now you can almost get perfect FID. FID lower is better. So you're almost getting 0 FID, which means perfect match of visual quality of test generated images to the training images. But that doesn't mean, right, that we are anywhere close to being good at image generation, because even simple things like a stack of 3 cubes or a nurse, right, you can see a lot of challenges here. Spatial configuration and fine-grained reasoning skills, or things like social biases, right? All of this cannot be handled by just FID looking very good, right, close to 0. So this is where we basically proposed the first DALI eval model back 2 years ago, and we've also updated it since then in several versions to add more and more information. But the idea was, can we have an evaluation method to probe the reasoning skills and social biases of text-to-image generation models? And the basic idea here is that when you take a generated image, can we do things like object recognition, right? If the prompt said photo of a dog, can I detect a dog? If it said photo of 2 dogs, can I detect 2 dogs? If the prompt said cat is left to the dog, did the generated image, if I find the boxes for the cat and the dog, did they respect the left relationship in terms of their coordinates, right? The x coordinate of the cat should be less than the x coordinate of the dog, which in this case is not true. So that's the basic idea, right? We created a very complex data set and very carefully designed data set called paint skills, where we have different kinds of configurations, counts, spatial relationships of objects, right? By treating this as a simulator generated control. And then this also allows you to create very new kinds of combinations of images that the model cannot just memorize, right? It should be able to do real understanding on this image and not just think that, okay, in most of the training images, right, something happens, so it should also be happening in the text, right? So it should not be lying about the evaluation. It should be doing real evaluation. So using this paint skills data set, now we can generate images and we already know what the ground truth should look like, right? And then we can basically try to calculate the coordinates to make sure that count, object, spatial, everything is correct. So some initial results here we saw were that, first of all, our metric DALI eval was consistent with human judgment. It also showed that different models are good at different skills. And finally, counting and spatial skills were harder for most models. There's also more fine-grained analysis, right? That counting larger numbers is harder, left, right, above, below were equally hard, right? These kinds of things. And then the paper also has a big chunk of contributions on the social bias evaluation, where if we have a lot of these prompts, which should technically be generating neutral kinds of images, right? We showed that if you say nurse, right, you want to make sure that the gender bias, the skin tone bias, and the attribute bias, right, these kinds of things should all be technically neutral. So the way you can do it is you can basically use skin tone, Monk skin tone analysis, right? With obviously you have to also include illumination awareness, those kinds of things. And then if you try to estimate these different properties on the set of images generated, what you want to do is you want to measure how skewed are the distributions. So the more skewed they are, the more biased they are, right? Whereas if it's a uniform distribution, then right, they are better at not being socially biased. So that's another takeaway here that you can check in more detail in the paper. But the idea is that we basically showed that min-DALI, like smaller models, actually were less biased than some of the larger models like Stable Diffusion and Carlo. And we also showed that some professions were much more skewed than some other professions. And then the last slide is about how to do a more interpretable version of this evaluation. And the idea here is similar to VP Gen, we have something called VP Eval in the same paper, where even for evaluation, you want to first generate a program. And then you want to basically decide whether that program, if you execute it, what is the score of the image and which parts did it get right or wrong. So suppose you're trying to evaluate, so I can just show some example here. If the prompt is a prompt of a dog, then the program should be something like object evaluation. If it's 3 dogs, it should be a count evaluation program. If it's a spatial kind of prompt, spoon is in front of a plant, then it should do a spatial evaluation program. And the programs are defined here. Like spatial evaluation will check for X coordinate if it's right. And if it's in front of something, that will check for the Z coordinate. If it's right on the top of something, it will check the Y coordinate and so on. So basically what the language model's job is that it will convert each of these prompts to automatically decide which program should be called. And then it will execute that program. And then it will tell you that, okay, there are 3 objects called dog in this image, but in this image, there are 5 object dogs, not 3, things like that. So it will also explain to you what the error was. And then you can also do this for a multi-scene kind of scenario where you have a very big prompt, like white slope covers the background, while the foreground features a grassy slope with several rams grazing one measly underdeveloped evergreen. So this can automatically generate multiple things to evaluate, like ram presence, evergreen presence, multiple rams, but only one evergreen, right? And then you can again run all of these and show that which parts did the image get correct and which parts were wrong. right? So this is a much more interpretable and explainable evaluation process where you actually can control this program. And when you execute it, you also get errors, right? Which ones were correct, which ones were wrong. So let me skip most of this now. I think we got the main idea, but in interest of time, here is sort of the last slide on some things that I talked about and some sort of related big challenges, right, that are important to think about, right? So I already discussed unification of right models versus specialized models. We should also be thinking about right strengths versus limitations of large-scale pre-training. We all know the strengths, right? But we should also focus on what kinds of biases, right? Fairness issues, data quality and imbalance, interpretability issues, right, that I discussed. There's a big open question on, right, whether we should use structured knowledge graphs, modular knowledge versus, right, just learn everything from large-scale pre-training. There's a lot of other modalities we need to think about, right? So we've already brought in 4 or 5 modalities, but there's things like non-verbal modalities like gestures, gaze, right, which we are looking at through our education institute, as well as action interaction, right? That's how we learn, right? If we get burnt, we know not to touch something hot later, right? If we bang at like our head against a ball, right, we are more careful next time. The last couple of things are about analysis and evaluation, right? So long distance understanding is very challenging still, right? I showed you that long distance generation is even more challenging, and also counterfactuality and causality, right? How do we know whether a model is doing something right for the right reasons, or is it just getting lucky, right? So can we do some counterfactual changes in the input to see whether the answer changed or not? Yeah, anyway, I think I leave this slide on and then maybe pause here. Thanks.
All right. Thank you very much, Mohit. We are already like 2 minutes over the time, but I think we have a lot of burning questions in people's mind.
Yeah. Sorry. Yeah, I didn't realize. I forgot to ask, I guess. I thought maybe like a lot of places have questions after the 1 hour, but I should have checked whether this includes the question. But yeah, I'm happy to take questions, and I'm also happy to stick around for a bit.
So Cheryl, I think what I can do is I can try to ask like people on the Zoom, like if they have questions, and then for people who are in person, do you see hands raising? Like, do they have questions? You can just probably speak it out. Okay, I will start with the first question that I see on Zoom.
Yeah.
From T Nguyen, he's a new associate professor who just joined. Are your frameworks based on pre-trained models? And if so, how do you handle performance in data scarce domains like 3D robot motion?
Yeah, so that's a good question. So basically, yes, they are based on pre-trained models. So for example, if I take the example of multi-scene video generation, right, we actually show how to do good multi-scene generation without training on any multi-scene videos, right? Because that's the future. I mean, I think that's what you also mean, right? That you cannot really rely on data in data sparsity scenarios. So the way we do it is we use the power of large language models with a few examples to teach it, right, how to be able to handle multi-scene videos through consistency, and then stitch together, right, frames from single scene video generation. So that's maybe one example, right, of how we are handling like generalization of to new scenarios, but using knowledge inside large language models.
All right. Any question from the audience who are in person?
And then another example was the Cody thing, right, where we cannot assume that we have training data for all combinations of inputs and outputs, right? So that's where we showed how to do this bridge alignment, where you can mix and match different latent diffusion models to handle new combinations of modalities, right? Because that's exactly your question, that we will not have training data for, say, image plus audio to video plus audio, right? Like it's hard to have even 5 examples of this.
Okay, so Cheryl has a question. Do you think we will reach a point in the foreseeable future where we will run out of new data to train models on?
Yeah, I think it's already there almost. I feel like, right, and sometimes we don't even know what data is going in some of these black box models, right? So I think that's why my research has been focusing, right, as you saw, like the Cody example or the large language model planning example, right? We are trying to see how can we take the knowledge already in the largest pre-trained models that we have, but then, right, try to teach them how to do new tasks. I think to me, that's a big part of important part of the future, right? As opposed to trying to find more data, especially large scale data, right, which will be infeasible to teach any new task.
All right. Okay, we're looking for next question. Naman. Okay, so I see someone. Okay, go ahead. But we cannot hear anything.
And this is, by the way, my information on the last slide that I should have left at. So feel free to email me, and thanks to the awesome students, right, whose work I presented. And here's my contact information also.
Oh, I have a question.
Mhm.
There is no echo. So maybe you want to, I don't know, maybe mute your speaker and just have the mic. But now you are muted, so you have to have the mic open.
Yeah, now it's good. Echo. Maybe you can just type it.
Yeah.
What about, are you also joined on Zoom now?
No, we cannot. Cheryl, we cannot hear you. Can you just type it in, the question? And is Naman Bansal there? We have one more Bansal in our audience. So he usually has a lot of questions, but I don't see him asking questions. Naman, are you there?
I think there's a Zoom question. No, we can't hear you.
Yeah, so can you hear us? That's the last question.
Right.
So I don't know.
Okay, yeah, now there's a question.
Yes. Okay, so from Mahdi. So he's also one of my students. Okay. Can you share how are you planning to accommodate continual learning when we are taking help from already trained LLMs in the process of generating output?
Yeah, so that's one of the bullets I had in the previous slide. But yeah, so I was obviously not able to cover the continual learning stuff because I already had too much stuff to present. But we've been doing a lot of work on model merging and continual learning, which is basically efficient ways, right, that you can update the model or combine models knowledge without having to retrain anything. So one direction of work we are doing is called model editing, where can you make the model delete or unlearn some information, right, and replace it with new information, which is very challenging, by the way, because all the localization algorithms, right, that try to tell you where is a certain information stored in a model, sometimes, right, they does not mean that they will also tell you where to edit the model. And the other direction you can look at on my webpage is our work on multimodal model merging, where again, can you, if you have another smaller thing, right, a set of vectors or parameters that have some updated knowledge, can you merge this knowledge with the previous model, right, without having to retrain anything, as well as, right, you don't want to lose information on the previous tasks. So no catastrophic forgetting.
Okay.
Then there's one more question. Yeah, exactly, unlearning. And then
LLMs are very good at planning, but not in the complex scenarios. For example, reverse poem generation. So did you see it fail in the very first step in your 3 planning papers? Also in diagram GPT-4 is very bad at generating words in images. Did you use LLMs? Did your used LLMs work well, or how did you evaluate the goodness of your diagram GPT?
Yeah, so I went a little bit fast on that part, but the idea here, as I mentioned, is that you basically, we already showed, right, how DALL-E 3 and in fact even GPT-4 vision version, not just GPT-4, we showed is not really good at any of these tasks, especially diagrams, right, which are very, very fine-grained and dense layout control. So that's why we have been pushing a lot on this idea of how to use language models to generate layouts, right? So which is what the 3 papers were about, but with different aspects, right? So if you see the paper, like I said in VP Gen also, right? In fact, the prompt to layout generation part is very accurate. The bigger problems are in the layout to image generation part from things like Lygen. So yeah, so hopefully that answers part of the question. And then for the evaluation of diagram GPT, I briefly showed you, we have a huge table with 7, 8 different kinds of metrics, right, for diagram evaluation. One is about image similarity, one is image and caption similarity, right? One is caption similarity, and then FID, FVD, VP eval. We also check the layout accuracy. So those kinds of things.
Okay, the second Bansal is here now. Hi, Professor Naman here. My question is as follows. Number one, right now, much of the research seems to be focused on training large models and just increase the model size and data samples. Do you think that's the way forward? I think you have already answered this because
I think none of my papers are about that. So that's hopefully a good, I mean, yeah, you're agreeing with what I showed.
Yeah, or do you have some ideas on the smaller models with similar capability? I think you have already,
Yeah, so we have also, like I said, some other papers that I didn't cover today, right, on how you can actually do a lot of distillation and compression and model pruning, data pruning, right, to be able to actually get same performance as much bigger models. But the other angle that I showed today is also how you can take existing models, right, without bringing more data or more size and make them do very new tasks, right, that they're not developed for.
Yeah,
but I can do follow up. Yeah. Mm-hmm.
Yeah, I have a question because I don't have a lot because I went through your talk in the in workshop. So I have a new question now. So here is the questions. If your prompt has got something, is asking for something that needs some predictive power. For example, generate me an image of Seattle City maybe next week. Maybe what's the weather condition that will make an impact on the image that you generate. So
yeah, so I think Cody could technically handle that, right? Because if it has, if it has access, right, to the tools and the web, then the text part can basically be a sentence about next week's weather, right? It can go to weather.com and send you the text, all the information from the weather. And then, right, your image of Seattle was already there. So now it can update, right, the image of Seattle to make it more sunny versus more rainy. So that's kind of right similar to what we saw for the Times Square image. If we just sent it an audio clip of rain and it's made all the floor the floor wet.
What about cases where you don't find that information publicly, but you have some private data and you need to actually build it to a time series model and predict what is happening?
Yeah, so that would be interesting. I think new research. I don't think current models can handle that. But yeah, I think that's related to the learning part, right? Like, can we basically have models that are outdated or at least need to, right, predict like how the data will change, right, without relying on the new data? Yeah, so that should be cool.
But yeah, I mean, these are so much work. Can you tell us like how many students in total, like a rough number, like contributed to this your all these?
I think this is probably 8 or 9 students. But it's one theme of our lab, right? We also have big talks or themes on explainability, and then we also do a lot of work on efficiency. So the multimodal aspect is probably 7, 8 students. Obviously, some of them have graduated, right, for the older work. Yeah, so the students are doing all the great work. So all the credit to them.
I mean, credit to you as well. I mean, you have to like
hopefully I'm some small contribution.
No. You have the overall picture, right? So, any other questions from the audience? And of course, you can reach out to
reach out to me. I know it's already late, so just feel free to set up. Send me some emails, ask questions, set up a meeting.
Okay, looks like we are good. Cheryl, we are good.
We can give him a hand.
Yeah.
Great. Thanks a lot. Yeah, thanks for having me.
Mohit, and then Mohit, I'll catch up with you later. Awesome. Thank you very much for again accepting our invitation and giving a wonderful talk.
Thanks. Yeah, appreciate it.
I'll pause the recording now. Okay. And then thank you.
Thanks.
I'll see you in the next AI at AU forum meeting. See you. Bye-bye.
See you. Thanks. Bye.